It's like run is only one of
That's the
ours.
Ruga.
Right, Greg?
Huh? That's a Ruga.
You would say run.
All right. So I guess that's right. So we began speaking about zeros and poles. So remember the last thing we proved. If Z0 is 0 of f, then f of z can be written as z minus z0 to the power of n times g of z in some neighborhood. Of z0, and we know that in that neighborhood g of z never vanishes. And the integer n is the order of the 0. Another word for it is multiplicity. Yep. So again, the intuition behind it is very simple. If it's a holomorphic map, then it's locally a polynomial. And if it's a polynomial, then if you have a 0 at some point, then you can factor z minus z0 or z squared minus z0. You can factor some sort of order of the prime polynomial z minus z0. Okay? So this is what this n is unique. And we also prove that it's unique. So then what we next have is another view of poles. So a pole, it means that limit as z goes to z sub 0 of f of z will blow up to infinity. And maybe that's very, very natural to call it a pole, because it's as if you have, from the plane, you have a stick coming out. And around this piece of paper, the conformal map is just bending around it and blowing to infinity. So then we can say the following. Another way to look at a pole is we can say that if 1 over f of f is holomorphic, in a neighborhood of z0 and limit as z goes to z0, 1 over f of z will be equal to 0. If f of z blows up to infinity, 1 over it will have to go to 0. Agreed? And we would say that 1 over f is equal to 0 at z0. And you can say that this 1 over f of z is holomorphic at z0 as well. So you can think of a pole as if you have a neighborhood in which 1 over f is holomorphic. So there is a very similar corresponding theorem for the multiplicity of the pole because of that fact. Because if it goes to infinity, 1 over f will be then holomorphic in a neighborhood. That's our way of looking at it. And then we expect a similar result to to the theorem that we proved. So this is it. Theorem. If F has a pole at Z0, then in a neighborhood of Z0, there is a non-vanishing holomorphic function. H and unique integer n bigger than 0 such that f of z is equal to z minus z sub 0 to the minus n times h of z. And h does not vanish. Now the proof is pretty much immediate. So you understand our definition of a pole? I mean, really this is equivalent, but we haven't described Riemann removable discontinuity theorem. So in essence, for our definition is going to be that we have a pole if 1 over f is holomorphic in a neighborhood of z0, and as you push the limit to the 0 to z sub 0, you get 0, and the function is holomorphic in the entire region. All right. So the proof is that 1 over f of z is holomorphic in some set dr of z0. That's a neighborhood of z0. And we know that 1 over f of z0, I can think of this as 0. Hence, I can apply the theorem there. I can take 1 over f of z, and I can factor it. I can write it as z minus z0 to the n times g of z, where g of z does not equal to 0 in the neighborhood. Yep. Agreed, because it's a holomorphic map, so it has a 0 at z sub 0, and therefore that can be factored, and that obviously implies that f of z is z minus z0 to the minus n times 1 over g of z, which is another holomorphic map, which is our z minus z0 to the minus n times h of z. And the proof is complete. Immediately follows. All right. So here is a theorem regarding a pole. If f has a pole of order n, at z0, then, well, I haven't really written to you what's a pole of order n, but that's very clear, right? This n is unique, so that would be a pole of order n. So if it's a pole of order n, if you can factor z minus z0 to the minus n, and that representation is unique, then f of z can be written as some a sub minus n over z minus z0 to the n plus a minus n plus 1 over z minus z0 to the n minus 1 and onwards until we reach a minus 1 over z minus z0 and then plus some function g of z where g of z never equals 0 in a neighborhood. Of z0. Now, so that I don't have to put it later on as a definition, this thing here is going to be called the principal part. So this thing here, this is P of z, and that's principal part of f near z0 or at z0, whatever you like calling it, right? So the reason we're going to pay attention to the principal part is, again, we're interested in integrating holomorphic maps over closed curves. So over closed curves, you can see this has an antiderivative, vanishes. Everything in this, every holomorphic map has an antiderivative. So everything vanishes except for this part, okay? And that would be the residue. So the principal part is important in integration because of that. So let's prove that theorem. The proof is very easy. Proof. So what we have is that f of z can be written as z minus z0 to the power of minus n times a holomorphic map h of z, where h of z is holomorphic. So if it's holomorphic, it has a power series expansion. So I can write this as z minus z sub 0 to the minus n times the power series expansion. I call it a0 plus, and I know this is, by the way, not 0 because locally this map has no, it's not vanishing, right? a0 a1 z minus z0 onwards. So let's say somewhere it's going to be a sub n z minus z0 to the n, and it continues in that fashion. So if I distribute, what do I get? I get a0 over z minus z0 to the n plus a1 z minus z0 to the n minus 1 plus somewhere here would be a sub n minus 1 over z minus z0, and then a sub n plus a sub n plus 1 z minus z0 and onwards. Yep. So you already see the principal part emerging, and then you have, this is our g of z. Easy, right? So just power series expansion locally at z0, and we have that. All right, and again, the importance of a principal part is the following. So again, principal part is important in integration. So I'm going to illustrate it by a picture. So here is some arbitrary circle C. Let's say I'm going to orient it counterclockwise. And the circle, of course, is completely contained in the region omega, where f is holomorphic. And I'm interested in integrating over C the function f of z dz, where this function, it does not have to be holomorphic on the interior, right? So then what do I do? Well, let's locate the point z0. In other words, imagine that in the circle, the function is holomorphic everywhere except at z0, where at z0 it has a pole. So let's say the pole is here. So what we can do, we can just then go about it, and we can create a corridor. So this is the corridor here. And you can see it's, and again, the corridor is centered at z0. So what you can see is that by Cauchy theorem, this is, and this is, let's say, of radius epsilon. So this is C of radius epsilon centered at z0, right? So then by Cauchy theorem, we have that the integral is the same as the integral over a circle centered at z0 of radius epsilon. But in a very small neighborhood, f can be written as the principal part plus g of z. Right? And this is completely holomorphic. So this vanishes. So really the integral is the same as that of the integral at z0. Right? Here I am assuming, of course, f is holomorphic inside C, except for a pole at z0. Okay, so then we can have this integral. Yep.
The last part, you said the g of z vanished over there?
Yeah, it vanishes because this is a closed integral. So Cauchy's theorem shows that if we have g is holomorphic on the interior of this circle. So Cauchy's theorem in the circle or in the disk, right, tells us that every holomorphic map has an antiderivative. That's in essence what's the consequence, right? If I have a function that is complex differentiable inside of a disk, then if you take any circle inside of the disk, such that the interior is also inside of the disk, of course. Then it has an antiderivative there. So g of z will vanish, and then we have the integral of p of z. And what's the integral of p of z? The integral of p of z ends up just being the integral. Each of those parts, they have antiderivative, because for them you can just quickly come up with an antiderivative, right? 1 over z minus z0 to the n, you know the antiderivative for it. So in essence, what ends up happening is that the integral of p of z dz itself is reduced to the integral at the a sub minus 1 term of the pole. And what it ends up being equal to 2 pi I, because integrating 1 over z minus z0 over a circle is 2 pi I times a sub minus 1. So you see, I mean, in complex integration, what plays a huge role? 1 over z, right? The integral of 1 over z, the logarithm. I mean, you don't have necessarily a logarithm. You might have a branch of it. We discussed that later. But that's really what plays a huge role in integration.
And the only reason we end up with a residue over there because there was a pole over there. If it wasn't
yes, I mean, if it's not a pole, then actually what can happen, I'm not sure. It can be really scary, right? If you don't have a pole, we're going to see later examples of functions where the singularity is not a pole, but it's called essential singularity. So if it's not removable and it's not a pole, it's going to be called essential singularity, and there are consequences to essential singularities that are very different. Right? So, yep. So then, first of all, we are going to call a minus 1 is going to be called, in the language of Stein, but also in any residue, at the point z sub 0 of f, something like that, right? That's called the residue. So you see, in other words, if I have some means of finding this coefficient a sub minus 1, I very quickly can determine the integral. Yeah, but you will see how pleasant it is to do residues. Maybe you have already, right? All right. I was doing one on the train. Everything works except for one error that I cannot get. I mean, I don't know what's the error. Maybe you'll catch me, right? I know there is some error. I think that there should be a 1 appearing instead of a 3, but I see a 3 all the time. You know? So yeah. So anyhow, so determining the value of a minus 1. In theory, very easy. The value so it's very nice if it's a simple pole. So a simple pole, you know what it is, right? So 1 if ZZ is a simple pole. I think I haven't defined it, so a simple pole means that that f of z is equal to z minus z0 to the power of minus 1. So it's of multiplicity 1 times h of z. Okay? You understand what it means, right? So simple pole means that the multiplicity of the pole is 1. And that's really what you really hope for when you do integration. Because if it's not, yeah, then a sub minus 1 is equal to limit as z goes to z0 of z minus z sub 0 times f of z. And the reason for that is because what do we have? We have that f of z if I had to represent it, will equal, if it's a simple pole, to a minus 1 divided by z minus z0 plus some function g of z. Right? The principal part is really short if it's a simple pole. So what does it imply? That implies that if I multiply this by z minus z0, I get to isolate a sub minus 1 plus z minus z0 times g of z, which then is moving towards a to the minus 1 as z is moved towards z sub 0. Makes sense, right? That's pretty clear. If it's a simple pole, this vanishes, and here we have isolated a sub minus 1. Right? So theoretically, we know that if we have a simple pole, we have this representation for the function f of z. Now, how do I get to a minus 1? I see that I need to multiply both sides of the equation by z minus z0. And then you see that on this side, you should be getting a minus 1. So that tells you that without knowing how this part looks like, all I need to do is multiply f of z by z minus z0 and take the limit. Easy, right? Now, let's see what we have to do if it's not a simple pole, if it's a pole of order n. Two, if z0 is a pole of order n, then what do we have? Then we have that z minus z0 to the power of n times f of z. What would that be equal to? That would be equal to z minus z0 to the power of n. And you see we have a pole of order n, so we would have a sub minus n over z minus z0 to the n, all the way to a minus 1 over z minus z0 plus g of z. The principal part is a little bit longer. So if I carry out this multiplication, what do I see? I see a sub minus n plus a sub minus n plus 1 times z minus z0, and all the way to a minus 1 z minus z0 to the power of n minus 1 plus z minus z0 g of z. Agreed? Now, I'm not interested in the other coefficients. I only want to have a sub minus 1. Right? So then, observe what happens. The first part, the principal part, became a polynomial of degree n minus 1. So if I differentiate it n minus 1 times, I will isolate a minus 1. And there would be this extra, I forgot to have the n here, this extra thing that I will have to also differentiate n minus 1 times. So we can see that if I take the derivative n minus 1 times of z minus z0 to the n f of z, then what I will get is n minus 1 factorial times a minus 1, a sub minus 1, I mean, plus the derivative of this n minus 1 times. Or n times, actually. N minus 1 times Yep. Now, if I take the derivative of this n minus 1 time, derivative works like multiplication, right? It works like the binomial theorem. So each term in this it will be a sum of n minus 1 terms. If you want to, I can even write that sum. Let's actually write that sum. Just it's actually a little ugly the way I wrote it, but maybe it's so. This derivative will look like k equal to 0 all the way to n minus 1 of the derivative d dz to the k of z minus z0 to the n times the derivative d dz n minus k minus 1 of g of z. Right? That's how the binomial theorem will take the derivative here. And the implication in any case is that limit as z goes to z0 of the n minus 1th derivative of z minus z0 times f of z will give me n minus 1 factorial times a minus 1. You see, because this will, in this derivative, there will always be z minus z0 term. At the very worst, it would be z minus z0 to the power 1. So the implication is that a sub minus 1 is simply equal to 1 over n minus 1 factorial d dz n minus 1 z minus z0 to the n times f of z. Okay. Good? So now, again, let's briefly talk about the residue formula. So we have the following theorem. Suppose f is holomorphic in the region omega containing circle C and its interior. And the exceptions to that is for poles at Z1, Z2, Z sub capital N. By the way, can this map have infinitely many poles? Could F be holomorphic in the region? You see, I said that we have finitely many. Could I have inside of a circle infinitely many poles?
No, because it would spread
Yes, you're right, no, right? If we have infinitely many poles inside of a bounded region, that implies that there is a convergent sequence of poles. And convergent sequence of poles implies that 1 over f of z has convergent sequence of zeros. That would imply that the function f is identically infinity. You see? Because 1 over f will be identically 0, so f will be identically infinity, and there is nothing interesting about it. But we can have infinitely many poles over the complex plane. That can happen.
Even
right?
finite?
No, infinite inside of a complex plane. You cannot have infinite inside of bounded region. Right? They have to be spread apart. They cannot cluster. They have to be isolated. That's the issue. Okay. The end. Then we can say that the integral of the function f around C, around the circle, will be equal to 2 pi I times the sum of these poles, times the sum of the residues, to be precise. All right. So we actually already proved it, but I'll just sketch it again, right? Proof. So we have a disk. And inside of the disk, we have a bunch of poles. So what can I do? I can just I can create a multiple keyhole region. So here is, let's say, the point Z1. So what I do is I create a corridor to get to it. If I find another point, let's say here is the point Z2, I will create a corridor and get to it, and etc. Right? I mean, finitely many, you can say too. So if the circle is oriented counterclockwise, then the regions in the corridor will be oriented clockwise. Agreed? Agreed? So by Cauchy's theorem, by Cauchy's theorem, integral over C of f is really the same as the sum of the integrals where I can select a very small radius epsilon and the center is at the poles. Now, once with each of those separate integrals, we have the principal part representation inside of the small disks, and that will translate right away to the 2 pi I comes in from the residue, right? So this is just simply summation k equal 1 to capital N, and the integral happens to be z minus zk residue sub zk of f dz. because everything else vanishes inside of that small region. And that is where you get the summation to 2 pi I. I can factor the 2 pi I out. Yeah. So that's the idea of residue theorem. Once you have all those representations, it's pretty simple. It's a little tedious to work it out. Could be very tedious, actually. But so they always routinely ask at least one residue question on a qualifying exam at the graduate center.
Just a computation.
It's just calculation. They don't ask you to prove it. They ask you to calculate the integral using the residue method.
So even a proof would be on. A proof like that would actually be a hard question on those qualifying exams?
No. I mean, a proof of that. It's not hard. The reason they might not want to ask it is because you need to list a lot of details and whatnot, right? So on the exam they would never ask you to prove the Riemann mapping theorem. Why? Because it's a very difficult proof. It's long. You have to quote a lot of stuff, right? It's based on a lot of ideas. But they do ask you routinely, what does this theorem say, right? And they would ask you, there would always be some questions that are a bit interesting. Like something that you might not have seen before, and you just have to figure it out. But you have a choice, right? Usually you have a choice on qualifying exams. You don't have to answer all the questions. You have to answer several from each section. So actually the qualifying exam for complex analysis is, in my opinion, the easiest at the graduate center. The hardest that I've taken was real analysis. I actually have questions posted if you want to see. Right, because for real analysis, a lot of people know it better and they ask harder questions. All right.
So there are only 2 types of exams over there? Just
no, there are, what, 6 types, I think? Or, let's see. There is topology, which obviously I wouldn't have taken, right? Yes. Maybe, a lot of people adore it. Maybe I haven't developed the taste really, right? But I avoid it all the time. So topology. Then the other one is real analysis, complex analysis, abstract algebra, differential geometry. People are afraid of differential geometry, right? Those are 5, and logic is the 6.
No, but you don't have to take all of them, right?
No, you have to take 3.
3.
You choose your 3. If not for, I took algebra because algebra is, I guess, fairly accessible, right? But probably I would have preferred differential geometry, more interesting to me, right? So I like analysis. So I would have taken real, obviously, complex, obviously, and differential geometry. But I haven't. I just took whatever is. They say differential geometry is hard. I didn't take it.
and these 3 exams you can take it after completing 2 years of sequence of.
You can. That's the thing. You see, I wasted. I don't want to say that, but again, 2 years, right? When did I prepare? It takes. I don't know. Over the summer, I taught myself complex, and I passed the exam. Over the summer, I did for the real and passed the exam, right? If you are prepared, and you can be prepared. If you look on my website, I have a lot of questions that I took from those qualifying exams and answered them in detail. And you can prepare for real analysis exam. Of course, you never know what you can get, right? It's like a box of chocolates, right? So you don't quite know what in algebra, you don't quite know what you can get. But usually, complex analysis is a safe bet because if you know the 3 books that I mentioned there, with Alfors, they also like Alfors, right? And sometimes something else. But actually, if you read Stein and you read Conway, I think you will be more. Even if you don't have to read Conway, just know some sort of things there. You will survive the complex, and then pass the exams right away if you go there. It will be saving you a lot of effort.
But you still have to wait for course to complete.
Yeah, again, maybe I'm wrong, but because I'm not sure what sort of other pressures you will get, right? Okay. But you're supposed to pass them in 2 years. I guess if you pass them very quickly, you advance to the next level. Maybe they leave you alone. Maybe.
Do you have it?
They do. You see, because as soon as you pass the exams, you can carry over your credits from this school. You would carry 30 blanket credits. Right. But they do make you take what I forgot how many, 80 or 70 or 90. I don't know. Tons and tons of credits that you have to take.
But do they give you second choice? By the way, if you can't do it like in the first shot?
No, you have 2 trials at most for each exam, right? So if you fail an exam twice, you cannot take it again. All right. So yeah, so let's do examples of residue, right? So residue calculus. So I mean, for your practice, I guess I'll give you just do all the Conway examples and all the Stein examples. You just do a lot of them to be trained for it, right? So that you can quickly do them on the exam. But on my exams, you always have a choice, at least as far as I can, as far as it's up to me, you always have a choice to avoid it. So residue calculus. First easy example. So let's calculate the integral from minus infinity to infinity of dx over 1 plus x squared, right? So in calculus 2, you just right away say, well, that's arctangent, and you can just calculate it, right? But we do that using residue. And an interesting thing to note is, look at it. This is a rational function where the degree of the numerator is 2 times less than the degree of the denominator. So whenever you have that situation, you can actually save time and not bother about the boundary. So how we're going to calculate it? So we need to, obviously, part of my closed curve has to be going around the x-axis, right? So let me show you what you do. So this means the x-axis. So first you define the function f of z equal to, well, in this case, it's obvious what you should pick as the function. Just generalize it to complex numbers. So it's that. And then the region that you are going to pick is minus r to r. That's going to be spreading. So it's going to go like this. OK? And let's call this gamma sub r. So the entire region is gamma sub r, and this part of the circle, let's call it c sub r. So whenever you have a rational function where the denominator is 2 degrees bigger than the numerator, you know that the integral is going to decay over c sub r. So so you don't have to verify it many times. So you see, in this case, the choice of the contour is fairly natural. If it's a rectangle, you would have more segments to check. If it's a circle or some sort of one curve, it's fine. And you have this. Now, where do you have, so inside of this, if this half disk is big enough, it will contain the number I, which is a singularity. The denominator has a singularity at I. It's a simple pole at I. So somewhere here we'll have I. And that's what we need to do. So I would say my first step would be compute residue. So what we do is, in this case, so we know that the residue of f, the residue sub I of f, it's a simple pole. You see that you can factor it as z minus I and z plus I, so it will be a simple pole. And that would be limit as z goes to I of z minus I times 1 over 1 plus z squared, which is just simply limit as z goes to I of 1 over z plus I, which is 1 over 2I. Agreed? The residue is 1 over 2I, which implies right away what? It implies that the integral around the gamma r of f of z dz. There is only one pole in this in the upper half plane. You could have also selected the lower if you preferred, right? It would just simply be 2 pi I times times residue at I of f, which is 2 pi divided by 2I which is equal to, so 2 pi I divided by I, which is simply equal to pi. So you know that the integral around this closed curve will be pi. Okay? So that's step 1. Step 2 will be to estimate basically you want everything to vanish except for the real part here, right? So observe that the integral over C sub r of 1 over 1 plus z squared dz. Well, if I parameterize it, that would be the integral from 0 to, not to pi, but to pi, just half of it. Of pi, and what you have is 1 over 1 plus e to the, sorry, not e, it's, yes, it is e. E to the what I mean is the parametrization of the circle, so it would be r e to the it squared times I r e I t dt. Now if I take the absolute value here, this is the integral from 0 to 2 pi, sorry, to pi of this is the same as I say I can take the absolute value here and I say this is 1 over r squared. It's actually divided by something slightly bigger. If you prefer, even r squared minus 1, and then times r dt, which is equal to pi r over r squared minus 1, which goes to 0. Now you see why you need to have degree twice, right? It's because the perimeter introduces an extra r, right? So we can show in general, if you want to take any rational function and assume that the degree of the rational function in the numerator is bigger by 2. Then if you integrate around the contour circle, then you would see that you would have a ratio where now the numerator will gain at most an extra power and still will be crushed to 0. So then you don't have to do this procedure, this annoying procedure again and again. If you see rational function degree top, numerator is 2 less than degree of denominator, you right away know it vanishes. So we have that this is vanishing, so the consequence is that the integral over gamma r, when you take limit as r goes to infinity, of 1 over 1 plus z squared dz is simply the integral from minus infinity to infinity of 1 over 1 plus x squared dx, which is the residue. Yeah? Yeah, maybe just. So how long do we have? We have another 15 minutes? 20 minutes. 20 minutes, good. So here goes. I mean, I can do another one that I solved that is correct, but I mean, since we're on the topic of rational functions, let's select another more complicated rational function and see, what can go wrong. So if you see some mistake, because I'm stuck with it for some reason, you tell me. here. So here is another example of a rational function. Let's say we integrate from 0 to infinity, and we have here x squared dx over x to the 4 plus x squared plus 1. So notice that the power on the numerator is 2 less. So you know that, that around the circumference CR it will be k. Okay? So then let's try to solve this. So first of all, what would you say is your function f of z? Obvious, right? So that would be, just take this real valued function, make it into a complex valued function. Now, maybe I'll write on the top here, from 0 to infinity, this is an even function, so I might as well expand it to the integral 1/2 of minus infinity to infinity. By the way, that's not the only choice. That's not your only choice, but that's a nice one. Okay, so we have the 1/2 there. So in order to integrate this function, I'm going to choose a very similar region to what I had before. And this is my gamma r, similar region. Now I need to calculate residue. And that's the annoying part. Everything else is easy. This will be k. Okay? So compute residue. So we have the upper half plane. So what we do is we first look at where z to the 4 plus z squared plus 1 is equal to 0. I need to factor it, right? So that is equal to 0 if z squared, you see I can look at it as a polynomial in z squared, if z squared is by applying the quadratic equation, or if you see something else, something better here, you know, it looks like the expansion for the cubic. If it's z squared, it's really in e to the I times pi over 3, if you see that. But by the quadratic equation, that would be z squared is then equal to minus 1 plus or minus root of 1 minus 4 over 2. Agreed? So we have that z squared is equal to, so it's equal to minus 1 plus root 3 over 2 or minus 1 minus root 3, and I forgot the I here, over 2, right? Now, what are those numbers? So minus 1 plus I root 3, this is e to the I 2 pi over 3. Do you agree? So this is e to the I 2 pi over 3, or e to the I, what's the other one? I think it is e to the 4 pi over 3. Do you agree? E to the I. So don't agree with me fully, because I think that somewhere in my calculations there was some sort of thing that is not working. So let's hope that we catch it. I was doing it on the terrain, and I don't know. I'm getting something, and I think that the something is almost right. So we have this. So then what is z? So that implies that z, if I take square root of that number, it's plus, so z is equal to plus or minus. If I take the square root here, it's going to be e to the I pi over 3. And the other possibility is plus minus e to the I 2 pi over 3. So that implies that f of z can be written in factored form as z squared. Let's actually maybe write the denominator first. In factored form can be written as z minus e to the I pi over 3, z plus e to the I pi over 3, z minus e to the I 2 pi over 3, and z plus e to the I 2 pi over 3. And we have z squared here. Yep. So then we need to calculate the residues. Which of the points are here? So e to the I pi over 3 and e to the I 2 pi over 3. So we have a point here and a point here. So we have two. We have two poles, if it's big enough, right? The other two poles will be below the x-axis, so we don't care about them. So then we calculate the residue at e to the, so we calculate first residue at e to the I pi over 3 of f. And if I multiply, I need to multiply by, so that would be really limit as z goes to e to the I pi over 3, z minus e to the I pi over 3 times f of z. And what I get is that this crosses out. So I will have 2 times e to the I pi over 3. Here I will have z squared minus I 4 pi over 3. So I would have e to the I 2 pi over 3 because I squared this number here. 2e to the I pi over 3 times e to the I 2 pi over 3 minus e to the I 4 pi over 3. Do you agree? Now this is important because maybe I made some mistake somewhere. You see, I just what I do is when I take the limit, all I need to do is cross out z minus e to the pi over 3. So this is eliminated. Now what is this? When I push the limit, it's going to be twice e to the I pi over 3. What is, and then I have this times that. I multiply first, so it's going to be z squared minus this number squared. So z squared is going to be e to the I 2 pi over 3 minus e to the I 2 pi over 3 squared, which is e to the I 4 pi over 3. Do you agree? So if I do this calculation, that's what I get. And what I can now do is I can factor out e to the 2 pi over I 2 pi over 3 from here and here and cancel. So what I have is 1/2. I can factor out an extra e to the I pi over 3 here, so it will be 1/2 times 1. And here I have e to the I pi over 3 minus e I pi, right? Which is 1/2 times 1 over, the number here is 1/2 plus I root 3 over 2 minus 1. Actually, here plus 1, I found a mistake. Plus 1, right? It's plus 1. Psst, we got it, right? That was the thing that I was sure is right. Okay, good. So yeah, now I think it's going to be okay. So what we have is this is simply 1/2 times 1 over 3 over 2 plus I root 3 over 2. When you multiply it out, so this is just 1 over 3 plus I root 3, which is the same thing as 1 over, well, actually, let's just flip it over so it's easier to multiply by I. So that would be 3 minus I root 3 divided by root of 12. Agreed? Which is 1 over 2 times 3 minus I root 3 over root 3. Good? So now let's calculate the second residue, and then we're almost done. Right? So the second residue is at e to the I 2 pi over 3 of f. And the second residue, what am I plugging? I'm gonna plug, so it's gonna be limit as z goes to e to the I 2 pi over 3 of z minus e to the I 2 pi over 3 times f of z. And again, this unpleasant thing is, and then we have, I think on the top we will have e to the I 4 pi over 3. On the denominator, we have, so this is the part that gets cancelled, right? So then we take this, we multiply, so we will have e to the I 4 pi over 3 minus e to the I 2 pi over 3 times times 2 e to the I 2 pi over 3. Agreed? Now we can factor out e to the I 2 pi over 3 out and cancel. And what we end up having is 1/2 times 1 over e to the I 2 pi over 3 minus 1, which is the same as 1/2 times 1 over, that would be minus 3, right? Minus, this minus that is minus 3. Correct? Not missing anything? Yeah, okay, thank you. Minus 3 plus I, so it's minus 3 over 2, I'm sorry, plus I root 3 over 2. And therefore, this is simply, once you take the, so it would be minus 3 minus I root 3 divided by root 12, which is 1/2 times minus 3 minus I root 3 over root of 3. Okay, good. So now what we know? We know that the integral gamma sub r of f of z dz is then going to be equal to 2 pi I times the sum of the residues times 1/2 3 minus I root 3 over root 3 plus 1/2 minus 3 minus I root 3 over root 3, which is, so the 3's, they cancel out. So what we have is just 2 pi I times minus I root 3, the 1/2, right? So good. Because this cancels, then we have 1/2 times I root 3 and a half, so it would be this. So altogether we have 2 pi times root 3. And now our original thing we need to multiply by 1/2. So the integral from so the integral from 0 to infinity of x squared over x to the 4 plus x squared plus 1 dx is equal to pi times root 3, because it's half of that. And here we know that just limit as r goes to infinity of the integral over c sub r of f of z dz decays to 0. And that's because the power here is 2 more. So if you kind of carry it out, you can, instead of carrying it out forever, you can just take an arbitrary polynomial, divide by a polynomial of degree 2 higher, and see that over a circle it decays. Okay, good. So yeah, so good. We caught the mistake. I was thinking, well, it's going to be embarrassing, but we caught the mistake. And this is still a simple thing. So they can give you examples like this on the exam. And next class, we do a few more calculations. And then we move on.